due in 280 yesterday.
Someone in the chat saying something.
Yes, I don't. Well, we didn't look at that. Oh, I can hear you. Yes. I was wondering because apparently I made an entire 280 lecture somehow with my sound turned off. So there's a video of me just
gesturing.
Yes.
Julie sign language.
And it was a semiconductor physics lecture, so there was a lot of waving around. Maybe they thought it was sign language. Okay.
To dub it.
Yeah. You had pre-lecture 16 due today on Flash. We're not quite there yet, but you don't have another pre-lecture for a really long time until March 23rd. So we're going to do semiconductor physics today, hopefully wrap it up on Tuesday and start Flash on Thursday. This is the schedule for the entire rest of the semester. And I think I got it in even with, whatchamacallit, even with being a little bit behind. What does it mean by optional final exam? Exactly what it says. If you like your overall grade in BB Learn, you can, with no rounding, you can take that as your final grade and not take the final. If you choose to take the final, then you could possibly pull your grade up. And you could possibly pull your grade down. So you get to choose.
Take the final at your own risk.
Take the final at your own risk. And there goes chat. Okay, good. And then I can just close that. So the next thing big thing that's due, well, you got a pre-lecture due on March 23rd. Project 3 is due March 25th. So that's the deadline for any regrades on Project 2. What we will do with Project 3 is take your Project 2, remove the equilibration circuit, and put in a sense amp instead. So you're going to need more pulse sources to drive it, and you're going to need to get more of the timing in there too. Ask me questions if there's something you don't understand.
My absolutely enormous equilibration circuit.
No, you could still make the transistors bigger in the other circuit too. That's just in case I do this on time next semester. Yeah, to make it faster. Because his equilibration was going, his equilibration when it was going from 1 to VDD over 2 was going really, really slow. And I noticed that, and it annoyed me, so I told him to make his transistors bigger, and that sped it up.
Yeah.
So he could actually run it down to 2 nanoseconds of a delta. Okay. What are we doing? Holes are definitely real particles. As I have convinced the sophomores, holes have mass, effective mass, not real mass. They are the absence of an electron, and we have to treat them like they're real in very many different ways. So just think of it as being an empty space with a positive charge.
An empty space that has mass.
It has a positive charge, and maybe the positive charge is heavier. I am a little behind. Well, this is why pseudo spring break is helping us out this year.
That's when we should watch Bill.
What? Okay. Okay. Not in class. Given the MOS, this is what we want to try to do. The physical structure of the MOS, and when we say MOS, there's a thing called a MOS capacitor, which is part of a MOSFET. It's the metal, it's the oxide layer, and it's a substrate. And it's the capacitor that we put positive charge on the gate, which draws negative charge from the body and creates the channel. So we're going to be talking a lot about the capacitor today. We want to be able to calculate the threshold voltage and the body bias coefficient and the various parameters of junction capacitance. So this is a periodic table. Remember from 280, and I just finished this like yesterday, all their semiconductor physics. What is in column 4 makes good semiconductors. They have the thing that's in common with all the column 4 elements, they have 4 valence electrons. So in order to reach the magic number of 8 valence electrons, they're going to form 4 covalent bonds with each of their 4 nearest neighbors. It's a very stable structure. The first semiconductor they actually used was germanium, and it was popular in the 60s, and then they discovered silicon was better. Silicon carbide is a common semiconductor for high heat applications, industrial, automotive. You see a lot of big silicon carbide transistors. Another way we can get that magic number of 8 is combining a 3 and a 5 and putting them in a crystal together. So gallium arsenide is really good for high frequencies. Indium antimonide, INSB, as we always called it, is good for infrared photodetectors. Another infrared photodetector material is mercad telluride. And that's 826. So 2 plus 6 equals 82. I don't remember. Yeah, I think it's in that little metal series in the middle somewhere. Okay. Well, these are all good semiconductor materials. And hafnium isn't used as a semiconductor. It's used as part of an oxide. It's an insulator. So that's how we make semiconductors. Then, okay, so if I got silicon, what I want to do is I've got 1 silicon atom covalently bonded with its 4 nearest neighbors. They are repulsive to each other because these are electron bonds, so they repulse each other. They move as far away from each other as they possibly can, and that would be a tetrahedral structure. This is the unit cell, and the unit cell is the smallest building block that I can put and just stack these together and make a silicon crystal. And this unit cell contains 1 silicon atom there, a fraction of a silicon atom there, a fraction here, a fraction here, and a fraction here. And those will get repeated across the crystal. This is what the whole thing looks like when I start bonding it together. Notice there's different planes of symmetry here. And this is important. I should just shut up. But if I cut the silicon crystal across this plane, it will actually, I don't know if you can see my cursor or not. If I cut it across this plane right here, it's going to have different properties than if I cut it across this plane. And there are very specific planes that when you order, if you order silicon blanks, they will tell you what plane they cut it in. Yeah. It's a big geometry problem. But the electrical characteristics are different from like a 100 and a 110, which is just which way the unit vectors are pointing when they cut the crystal.
What's when the silicon atoms like a kind of free floating off and not actually connect to the rest of the structure?
You mean like these? Like these?
Yeah.
They just, there's more of the silicon lattice later. They just didn't draw it in. Okay. So if I take that 3D model and I put it on something I can draw easily on a piece of paper, we have this bond model right here. Here's a silicon atom. It is bonded to, covalently bonded, sharing this pair of electrons between its nearest neighbors. Sometimes, if I dope them with phosphorus, which is N-type, I'm going to leave an extra electron behind, because phosphorus has 5 valence electrons. So when I form the magic number of 8, 5 plus 4 is 9, there's an extra electron floating through the crystal. If I put a boron atom in, boron's a 3, it's going to leave behind a hole because it doesn't have enough electrons to reach the magic level of 8. Okay, I hope you've all taken chemistry already, at least high school chemistry.
High school.
Yeah, okay, that's good enough.
They made me take Chem 1 and EE.
Okay, yeah, they did. Oh, okay, it's a new option.
Biology, chemistry, or introduction. much faster. But I'm sad.
Yeah, Jack waited until the last semester of his senior year to take Chem 151. He said it was great. He was a genius.
I
Okay, sorry.
I was just distracted because
Okay,
I was miserable in that class.
we got to keep going. We got to finish. We got to finish this. We got to catch up a little bit. Okay. When I have an N-type material, I'm going to have these extra electrons, and the extra electrons, all the valence sites are going to be filled already, are going to be in the conduction band. So they provide a lot of carriers that can conduct through the crystal. In the P-type, I have extra holes. The extra holes actually conduct in the valence band. So the extra holes are in the valence band, and they will conduct from down there too. Whether it's P or N, we get extra carriers. Some of the carriers are holes. Oh yeah, this is good. Okay, so this is from a book, and it's not this book, but it's this series of books. If you like semiconductor physics and want a good like senior level reading of it, not graduate level, this modular series on solid state devices, they're really good. They're about $4 or $5 a piece, and there's 8 of them. There's an entire book on the p-n junction diode. This is the one I've been trying to sell to people in 280, but there's another one on semiconductor physics, and that's what this particular slide is from. There's one on MOSFETs, and there's one on BJTs, and then there's 4 more that I don't know. What? Here. Okay, so this is what we do. When a chemist calculates the S&P orbitals for a silicon atom, they have very distinct energy levels. And this is for, and they can calculate these really well, but this is for a silicon atom in free space, which doesn't really exist, with no other atoms anywhere close to it. A singular atom in the universe. When we get down to having smaller and smaller spaces between the atoms, these p energy levels start to split and meld into these sp orbitals. And when you actually get down to the case where this is the silicon lattice spacing, as close as the silicon atoms get to each other inside a lattice, this is the viewpoint we see. And that's usually what we think about when we're doing semiconductor physics, is I have a band right here, and we don't really call it S&P anymore. It's just a band of mostly empty states. And I have this is called the conduction band. And down here, I have the valence band, and it is mostly filled with electrons. In order to get electrons available for conduction, I have to put an energy in here. There's this gap in here, and we call this the band gap. And this gap is the amount of energy it takes to get a valence electron into the conduction band so it's allowed to conduct. Now, things that can give you the energy to jump that band, you need something that's greater than the energy of the gap, first of all. You can use thermal energy. You can have it at a temperature other than 0 degrees Kelvin. You can use electric energy. You can put a voltage across it that excites some of the electrons and gets them into those upper states. And you could put light energy into it. So you would need a photon with energy greater than E gap. So there's going to be some minimum wavelength, no, maximum wavelength, minimum frequency of the particles of light that will allow it to conduct. Atomic energy levels. If I have a single, an atomic core with a single atom, each energy level can hold 2 electrons, one with spin up and one with spin down. And then the same thing here. As I move these 2 closely spaced atoms together, this energy level comes across here, pretend I can draw a straight line, and goes like this, and the energy level splits slightly. So now I could hold two electrons in this energy level, another pair of electrons in this energy level as you get closer together. That's part of the reason why those bands kind of bend and morph as the silicon atoms get closer to each other. Right. Yeah, we can take, if we have kinetic energy, potential energy, if I have kinetic energy and I add it to this, it excites the electrons into the conduction band where they have potential energy, and that potential energy could be released into real energy by having an electron going down and combining with a hole. The new idea on this slide here is there's a vacuum level. And this vacuum level is how much energy does it take to take the electron and entirely break it free of the silicon atom, the silicon lattice. So it's no longer part of the structure. It's like an electron floating in free space. There, if you put enough energy in there, that will happen too. Okay. What have we got here? Different types of materials. We've got a metal. These are really good conductors. What's going on here is these two bands, the valence band and the conduction, that's the valence band on the bottom. The valence band and the conduction band overlap. So I put a little bit of voltage across it, it conducts instantly. I don't have to put a lot of energy into this. Insulators have a really big band gap. All these states down here are occupied. In order to get an electron that's able to conduct, I have to put like kilovolts across the material. Rubber will conduct if you put enough kilovolts across it. Glass will conduct if you put enough kilovolts across it.
The big thing is enough.
Enough kilovolts. Air will conduct if you put like 4 or 5 kilovolts across it. I know that number, and they use that and it's actually the number isn't kilovolts. It's an electric field. It's kilovolts per meter or something like that. This is why we have spark plugs, and they work.
Because you begin to run megavolts now.
Megavolts, yes.
Then we're back to the future.
Now, then we have Hunter sticking his head in the door. In a semiconductor, the gap is just right. This gap is, it's comparable to the energy you would get from photons of visible light. It's enough so that if I put a reasonable amount of energy into it, not enough to melt the material, but a reasonable amount of voltage across it, I can cause electrons to jump into the conduction band and away from the valence band. But it takes some energy to get them to conduct. In 280 last week, I just told everybody, keep telling them Ni is just a constant, don't worry about it. And then I say, well, it varies with temperature and material, but for purposes of 280, we say at 27 degrees C, which is about 80 degrees Fahrenheit, which is room temperature in Phoenix, the intrinsic carrier concentration is 1.5 times 10 to the 10th per cm cubed for silicon. And I just say it's a constant as far as this class goes. But you can see it does change with temperature. You get a lot more carriers with temperature. If we took that down to 0 degrees Kelvin, the intrinsic carrier concentration would be 0 of all materials. Germanium has a higher carrier concentration, so it has a smaller band gap. And gallium arsenide has a lower carrier concentration, which means it has a bigger band gap.
Look at big transistor and
yeah, probably. Yeah.
Slides.
Yes, yeah. Because germanium was a lot easier to purify than silicon. Yeah. And there's still, like, even like in the 80s, there are a lot of germanium diodes floating around because they only have a built-in potential of about 4.4 volts. So you can get a smaller drop across them. Then the Schottky barriers took over, which were silicon metal diodes. And those have a drop of about 0.1 to 0.2 tenths of a volt. So you can put them in power circuits and you lose a lot less power across the diode when you're conducting significant current through it. There was, okay, I'm surprised I didn't say anything about this yet. Okay. This is the Fermi Dirac distribution. And what this is, this represents the probability that an electron state is filled as a function of the energy of that state. And there's this unique thing called the Fermi level. And it's in the equation right there. And when the energy of the state equals EF, this becomes e to the 0th, which is 1. 1 over 1 plus 1 is 1/2. So if E equals EF, that means the probability that a state is filled there is 1/2. So about most of that's like the halfway probability point. Most of the states below that level are full. Most of the states above that level are empty. And both Fermi and Dirac came across this separately. Fermi was at the University of Chicago underneath the stadium, just like the Mirror Lab in U of A is underneath the stadium. The stadium has such big pylons into the ground that it's a nice stable thing. The optics building at U of A has 9 sub-basement floors. Because you go further and further into the ground, you have more and more stability. They don't like vibrations. They really don't like vibrations. You walk into the building and you're on floor 10, basically. Okay, so the way this works, if you were at T equals 0, this is basically 1. So the Fermi level indicates that all the states are filled that have an energy less than the Fermi level. All the states are empty that have an energy greater than the Fermi level. That's the square wave, the T equals 0 Kelvin. As the temperature goes above 0 Kelvin, some of the electrons with a higher energy in the valence states jump over to the conduction states, and you get to start to see the smoothing out. At even higher temperatures, it's going to smooth out even more. So temperature plays a big role. And part of the reason why I had to run all my circuits at 35 Kelvin, and some of them I even had to run down to 4 Kelvin. And I was at Kip Peak. Yeah, I don't want to say anything about that. Okay, if we think about how the Fermi level adjusts based on the type of impurities we have. If we have intrinsic silicon or any intrinsic semiconductor, we haven't doped it at all. The Fermi level equals the intrinsic Fermi level, which is exactly halfway across the band gap. So what that's saying is this, that's a G. What this is saying is that most of the states below it are filled, most of the states above it are empty. If I dope this N-type, let's do N-type first because it's easier to explain. N-type, I put more electrons in the crystal. I put some of those group 5 atoms in there that have extra electrons. That means there's going to be more carriers up here, and then the valence band is still filled, which means the 50% chance of having a state being filled is going to move up. So for N-type, the Fermi level moves up towards the conduction band. For P-type, I'm going to have more empty states, which means the Fermi level is going to move down. I have less carriers in there. I may actually do this. I'm not talking about George Simmons and never mind. I should just keep my mouth shut. I may get through this today.
George Simmons.
What?
George Simmons.
George Simmons. He's an optical guy I used to work with.
Oh.
He could tell good Fermi stories. Okay, so the unit of a volt. A volt is defined as being a joule per coulomb. An electron volt, the difference between, and despite anything I say in the following slides about, well, they're just the same, it usually the math works out that I can just change the units and say, see, it's the same. An electron volt is a joule per unit charge. An electronic charge, a joule per Q. Yeah, the two of them are off by a factor of what, we'll get to some of the magic later, of 1.6 times 10 to the 19th, minus 19th. So this is Q, which is 1.6 times 10 to the minus 19th. Okay. How I pass modern physics is beyond me. I could never do the calculation. I just change it. It's volts, electrons, volts. It's the same thing. Okay. Yes, I did. I finally sat down and forced myself to do the calculations correctly. Understood the concepts. Okay. So the Fermi potential is the difference between the Fermi level and the intrinsic Fermi level. The intrinsic Fermi level is always at E gap over 2, divided by the charge on an electron, which is negative Q, negative 1.602 times 10 to the minus 19th. We can solve that for EF over EI. Well, that's not exactly solving that. The difference between EF and EI we can solve for as being KT times the ln of ND over NI. Now let's do this calculation and you'll see why I never get, okay. EF, I can do it, but I have to think about it. EF minus EI is KT, this equation right here. So KT, K is 1.38 times 10 to the minus 23rd. Its units are joules per Kelvin. And I'm going to put the units in here because otherwise I mess up the calculation. T is the temperature. It has to be in an absolute scale. And usually we use 300 Kelvin for room temperature, which is about 81 degrees Fahrenheit. And then we take the ln of ND over NI. ND is my doping concentration. So this is 10 to the 16th divided by NI, which is 1.5 times 10 to the 10th. They have the same units, so those units cancel out. And what I'm left with is I'm left with EF minus EI in joules. It's a huge number, hugely small number. 1.38 times 10 to the minus 23rd. But the units are, my kelvins cancel out, are joules. I don't want that in joules. I want it in electron volts. So I take the electron volts. An electron volt is Q, 1.6 times 10 to the minus 19th joules. So I divide this by 1.6 times 10 to the minus 19th, and I get 0.3. Oh, and I wrote this number. That number is wrong. That is entirely wrong. I was copying the wrong number. This is 55.5 times 10 to the minus 21st. It's legible in my slide notes if you want to pull that up. This is 348 electron, 0.348 electron volts. Now, if I want to calculate phi F, what I do is I change the sign of E minus. I can tell you what the answer is. The answer is negative 0.348 volts. Because I'm taking this number and I'm dividing it by a really small number, which is like multiplying it by a really big number, which makes this volts a more likely unit to come up with for the answer. It works. Julie logic. Phi F. I can plug the numbers in. KT is 1.38 times 10 to the minus 23rd. T is 300 Kelvin. This is 1.602 times 10 to the minus 19th. I'm leaving this as an exercise for the reader. Ln, I flip the Ln over, so I get a negative. I get the negative of the other value. The only thing I've changed here in this equation is now I'm dividing by Q. And that's what changes the units from electron volts to volts. The negative sign comes from flipping over the Ln. Now you believe me? The answer is negative 3.348 volts. Try that calculation for yourself if you don't believe me.
Ever so slightly unconvinced.
You're ever so slightly unconvinced. Okay. You get to do it on the homework. Homework 4.
Oh boy, let's do it like April 1st or something.
Yeah, but I would definitely look at these slides when you do that homework. You can start the homework now. You don't have to wait. EF minus EI, I flip NI and NA. And NA is going to be a larger number, so this is going to come out when I take the Ln of a number that's less than 1, I'm going to get a negative number. This is always going to be less than 0 electron volts. And when I divide it by Q, the units flip to volts and the sign changes. This causes the units to flip to electron volts. Flipping this over causes the sign to change. There's 2 separate operations going on here. K, ND, and NI. Okay, so Luke, K is Boltzmann's constant. If you look it up on the internet, you might get it in some crazy units like BTUs per Rankine. The one you want for semiconductors is joules per Kelvin. And that one is always, it's a constant of the universe. It's always 1.38 times 10 to the minus 23rd. ND is your doping concentration. So the people who are manufacturing the devices know how many atoms per cm cubes of impurities they've put into the device. So that you can usually find, or you can calculate it and tell the guys in the factory that's how many atoms they need to put in there. Ni is the intrinsic carrier concentration, and for silicon at room temperature, it is 1.5 times 10 to the 10th carriers per cm cubed. So it's a constant for 280, but it does change with temperature, and it does change from material to material. Pretty much everything in here, we're going to use 1.5 times 10 to the 10th. There's more. Okay. Okay. Okay, stop that. Doping. So this is a review from what we looked at in 280. Phosphorus is going to be N-type. Oh my gosh, I know that now. Phosphorus is going to be, and the P always throws me off. Okay, so phosphorus is going to be N-type, and boron is going to be P-type.
I think back in 3 I just committed that to memory.
Yeah, I couldn't. It's taken me years to do that. I've always what I do is I do my homework with a periodic table in front of me, and that's why I just got lazy and never memorized it. I would look at what it was. Now this mass action law, okay, let's start here. When I dope, okay, so this phosphorus is N-type. So on the inside of my diode, let me do this in a more orderly fashion. On the inside of my diode, my number, the carrier concentration, the number of atoms per Cn cubed of phosphorus that I'm putting in. Now this is N-type, so it is, we call it donors because they donate electrons. The concentration of donors I'm putting in, this is atoms. It's 1 times 10 to the 16th atoms per cm cubed. And what happens is virtually every single one of those atoms I put in is going to give me a free electron in the crystal. So this is going to approximately equal what I'm going to call little n on the inside. And that is the number of electrons per cm cubed. Okay. Now, one thing that they found is that the intrinsic carrier concentration, if you increase the number of electrons that you put into the crystal, the number of holes available is going to decrease because those electrons are going to want to recombine. And they've discovered that if you take the concentration of electrons and multiply it by the concentration of holes, you get a constant at room temperature, Ni squared, where Ni is 1.5 times, you can use this for all your calculations, 10 to the 10th per cm cubed. So I can use, if I know what N is on the inside, I can find P on the inside. P on the inside is going to be Ni squared over N on the inside. That's for the N side of the diode. For the P side of the diode, now I'm talking about Na. This would be Na up here. It's the number of acceptors. They can, sites, it's holes. The acceptors are sites where I can accept an electron into there. So for boron, we're talking about Na. Same thing happens. Every atom that I put in is going to produce a hole, virtually. So this is going to approximately equal the concentration of holes on the P side, approximately. Close enough, no one ever calculates it using anything different. And so now I can solve the mass action law for N on the P side is going to equal Ni squared over Na. And Ni squared, Ni is the square of 1.5 times 10 to the 10th. So something on the order of 10 to the 20th.
So, okay, yeah, 10.
Right. Because I see that on 280 exams all the time is people forget to square it. Okay. This is an N-type semiconductor. And I know that, okay, so this is my band gap here for silicon. It's 1.12 electron volts are the units. The intrinsic Fermi level right here is halfway between the valence and the conduction band. So that is about 0.56 electron volts away from the bottom, from the top of the valence band. I've doped it, and I've doped it enough that the Fermi level, the 1/2 level of probability that something's filled, has moved up closer to the conduction band by 0.41 electron volts. And we can get that by calculating EF minus EI. And we did that a couple of slides ago. When you calculate EF minus EI, it's KT ln N over Ni. This comes out to be 0.41 electron volts. So it's moved up a little bit further closer to the conduction band. you can actually dope silicon so heavily that the Fermi level moves up into the conduction band. And then things get really weird. This is called degenerative doping. And one of your, because the normal laws no longer apply. Degenerative, and one of your homework problems in homework 4, when you calculate that, you will get an EF minus EI that's greater than 0.656 electron volts. And you can flag that as degenerative doping, and I think that's worth some extra credit. Anytime you get a Fermi level that's outside of the, it's in one of the, either the conduction band or the valence band, it's degenerately doped. Review. This is where we're talking about silicon lattice spacing. We don't really care about anything else because we're just going to put the silicon atoms in a lattice. So we can use that to come up with this diagram. We've got a mostly filled valence band and a mostly empty conduction band. This is intrinsic right here. If the Fermi level goes up closer to the conduction band, that means I have more of these states filled, more electrons up here in these states. This is N-type. And if I go and I move the Fermi level down, I have a negative EF minus EI. This is going to be P-type. And that means that I have more holes in the valence band where they can conduct. And I should put a little plus sign in them.
And so it's when the EF is removed into the conduction band, right?
Yes, or the valence band. You can heavily dope it P-type too. Yeah, you can dope it too much. Yes. When you dope it too much, it kind of I don't remember exactly what happens. It's been 30 years since I took these classes, and I haven't come across it since then because it's not a thing people normally do. But it makes the rules not work anymore.
So if you need to work outside the rules,
you have to create your own new rules, which is what Dr. Ferry made us do on our take-home final. Reinvent the rules for this time. Yes. AKA, never mind. So I went in and put arrows in this today. If I have an electric field pointing in this direction right here, that means that positive charge is going to move in the direction the electric field is pointing. It's going to move from plus to minus. My negative charge is going to move from minus to plus. Electrical engineering sign convention says EE current. Says current's moving this way, which is like whole current. Physicists say current's moving this way. But it doesn't matter. You can just change the sign at the end of the problem and tell you. But what's really going on, plus to minus, I have the electrons moving from minus to plus because they're attracted to the positive charge. I have the holes moving from plus to minus. When I talk about this, the algebraic current, and this is for electrical engineers, what I'm saying from an electrical engineering viewpoint, I have to do that, otherwise I'm going to get it backwards. Who I am at the moment. Positive charge is moving in the positive direction, so my current density, and remember current density is just in amps per meter squared, or centimeters squared, or whatever unit I'm going in. It's related to current, but it's like current per unit area. So if I have a bigger conductor, I would still have the same J as if I had a smaller conductor. So you can change the size of the diode and the J doesn't change. J sub n, because it's negative charge moving in the negative direction, the negatives cancel out, and Jn also moves in this direction. So the hole and the electron current contribute to each other. And the total current density is Jn plus Jp. They add together because we have charge moving in other directions. Okay, I got to step this up a little bit. We already did this. Spatial distribution, if I have, sorry, too much dust. If I have a high concentration of P charge, my holes are going to want to move away from the high concentration, not just due to electrostatic repulsion. So the holes want to move in this direction. And the electrons want to move in the other direction. The way the diode is set up is you have a spatial distribution of charge that's opposite of the electric, in a direction opposite of the electric field. So the drift current and the diffusion current exactly cancel each other out at equilibrium. That has to happen. And anyway, I got a better slide later. Okay, I should just shut up. Yeah, we just did this. You can look at this. These are going to be N-type. These are going to be P-type. This is a slide was sponsored by Medtronic, another of our corporate sponsors. But it's important. It's an important time to take a break too. We've been doing too much physics. If you want to get a job, there's not the key skills they're looking for. Employability are statistics, work experience, get some well-rounded like activities, join IEEE, volunteer, get some work experience or community experience. Communication skills are critical. And I think NAU does a much better job at this than any of the other schools in the state. We have that EGR sequence where you learn writing, you learn technical writing, you learn public speaking, and you learn to work in groups and understand basic project management. This is what you're going to be doing. Most of you is communications, writing reports, doing PowerPoints, maybe analyzing something, and then being able to show what the statistics are for the device you're analyzing. This is what you'll be doing. Not so much circuit analysis and calculating physics stuff, unless you go to work for somebody like that. There are jobs like that, but it's not, there's more getting work done, communicating with people, and getting the job done and analyzing what you have statistically than there is anything else. The big engineering breakthroughs are few and far between. I have a PN junction diode. On the P side of the diode, my P on the P side is going to be bigger than the N on the P side. And this number right here is going to approximately equal NA. On the N side of the diode, this number here is going to approximately equal ND. Notice there are not 0 holes on the N side. There's just a lot less of them than there are electrons. And there aren't 0 electrons on the P side. There's just less of them. They call these two down here, these are called, this is a minority carrier. And sometimes minority carriers become really important to make devices work, particularly BJTs. Don't work without them. So that's another thing that shows up in the physics books. Oh yeah, I added this to the 280 slides because I sort of, remember what we have at the PN junction? We have a depletion region. This is the P side. and this is the N side. And right at that junction, we have an area on the P side that has a whole bunch of electrons accumulating because the electrons from this side are attracted to the holes over there. Same thing happens on the N side. You get some holes over there. The area of those two squares will be the same to maintain charge neutrality. I believe this is Poisson's law. Who's taking the EMAG? Who wants to yell at me?
It might be Poisson's. No, I don't think that's Poisson's.
It's something. Okay, so it's one of Maxwell's equations, like Poisson's. I don't know. It's one of the electrostatic. It doesn't really matter. The idea is if I take this equation and I move dx over to the other side and I integrate it, I'm going to get the electric field. So, and this is the charge concentration right here. So if I integrate the charge concentration, I get electric field. And we notice that it goes up until I get to here, and then it goes back down to 0. Next thing I do is if I take this electric field that I've already integrated, and I integrate it again, I get voltage. And there's a negative sign in there. Okay, I was close. And I didn't even look that up this morning. If I integrate electric field, I get voltage. So what actually happens here is I get a curve that looks like this. As I integrate this, the area under that curve gets bigger and bigger, and I get a voltage, but this is my voltage versus X. V versus X. So this is where the built-in potential across the junction comes from. I have to have a voltage that's causing current to go in the opposite direction of the diffusion current, which is caused by those little charge blips right there. Is another way of thinking about it. And what this does to the bands, when we draw the energy bands in a diode or anything, the convention is you make the Fermi level your reference level. So if in the p-type material, where the Fermi level is closer to the valence band, it's gonna my bands are gonna look like this. And in the n-type, the Fermi level's closer to the valence band. I keep the Fermi level at a constant level, which causes the bands to bend across there by amount of Q phi F. We're getting there. At thermal equilibrium, this is the diode sitting there in open circuit mode. There's no voltage across it. The drift current, due to the difference in the charge concentration, exactly opposite in sign and direction. No, the drift current's due to the electric field. So we have a voltage drop going through here, so you're going to get some. That's not right. I think I flipped that.
So it should be drift and diffusion.
Yeah, I think the drift and the diffusion should be swapped. The drift current is due to the electric field. Not a lot of the carriers have enough energy to get over the barrier, but exactly the same number as the carriers that are moving away from their regions of higher charge concentration. Boy. That's not that important. I put it in, what?
Oh, the previous slide always got that on this law.
Yeah. If I put a higher voltage on this side, I lower the barrier on the piece. If I put a higher voltage on the P side, I lower the barrier height. More of the electrons have enough energy as drift current. So I start to get more current in the drift direction, a constant amount of current in the diffusion direction, which means I have a higher current. Shouldn't rush through this. In reverse bias, the barrier height gets higher. None of the or very few of the electrons get through for drift. The diffusion electrons are going to move at the same rate. So we get a curve. Wait, how did I get there? I went the wrong way somehow. We get a curve that looks like this. I have a constant negative current. This is diffusion current. When I reverse bias it, and I just froze. I will be back. It has happened. We're on slide 36. This doesn't happen in here often, so just give me a minute.